Okay, welcome back everybody. Hopefully this all works. I spent quite a bit of time over the weekend trying to work with Camtasia a little more and get an external mic on my MacBook, but the Mac doesn't seem to work very well. So I'm still back on my old system. Anyhow, okay, so today on the menu, here on the top right you get a little recap of what we've done before. So intro, radial flow, the steady state equations for confined and unconfined, and then the last time we started the confined transient flow with the Thies curve, the curve matching method that we've seen in the last lecture. And so today we'll see another method to get to the same numbers, which is the transmissivity and the storativity of a confined aquifer using transient flow data or drawdown data in a well. And then I will introduce the problem with the leaky confined aquifers, and I will continue on Wednesday on that topic. Okay, so a quick reminder from last lecture. This is the drawdown equation. So the drawdown in the well equals the amount of water we draw, so the discharge of the pump, divided by the transmissivity of the aquifer, right? The ability of the aquifer to provide water to the well, right? So of course, if an aquifer has a lot of transmissivity, then we don't need to draw down as much, right? We don't need a pump so hard. So the drawdown in the well, the water doesn't go down as much for a high transmissivity, so it's inversely proportional, right? Lots of water flowing to the well, no need to go so far down, or no need to have so much suction. And then finally, the important part here is that Wells function. So today we'll delve into that Wells function and what it actually is, so we can, well, we already saw last time the U, right? That's how you get the transmissivity, the storativity, excuse me. But today we'll look at here the drawdown equals the same equation, right? The Wells function. Now if we rewrite the Wells function according to what it is, so at large times, or large enough times, and we'll see in a second what that is, we can approximate the Wells function with this expression here in parentheses, right? Minus 0.57 minus natural log of, and this is the expression for U we saw last time, R squared storativity for TT. So transmissivity and time. Again, U being the surrogate for time. Now we can transform this this term in parentheses here, which is reproduced here, right? We can transform that into just something simpler, I guess, that you have here in parentheses. Just a quick note, 2.3 log 10 is the same as a natural log, okay? So this is just a transform. Another note in MATLAB, for those of you using MATLAB sometimes with my codes, log in MATLAB, the expression log means actually natural log, not log 10, okay? So it's different. If you want a log 10, you actually have to write log 10 in MATLAB. Anyhow, log or natural log of 177 is 0.57. Okay, so 0.57 here we can replace by natural log of what is it? 1.77 with a minus in front. Now the other thing with the logs, right? And again, I have those automatically moving somehow. You'll remember that log x plus log y equals log of xy, right? X times y, right? And then if this is a minus here, then this is a divided. Okay, this is just the log affinities or laws. Okay, so now we can replace this by, again, minus ln 1.77, which means we can throw this number here on the bottom, right? It's a minus, so we can divide here, so it's the same as log of this divided by 1.77. And if you do 4 divided by 1.77, which is here, you get 225, right? 225. So you can replace this whole expression by either 2.3 log 10 or natural log of 2.25 kb, which is transmissivity, time divided by r squared over s. Again, remember that I changed the signs here, right? So 4 divided by 1.77 is 2.25. So the 4 is gone, and this is all replaced by this, and then kbt over r squared s. Okay. Oops, sorry, didn't make the main point. So now we can plot this in a straight line. Okay, so you can see that if we log the x-axis, so this is the x-axis here, time is the x-axis, right? Remember, time or slash or 1 over u, but if we have a log on the x and a linear scale on the y now, right? So if we do a linear scale for s and a log scale for time, and again, this is equivalent to a linear scale for the Wells function, if you will, and a log for the u, right? The 1 over u, I should say. Now, if we have a semi-log x, so a log only on the x, not on both, just on the x, and a linear scale on the y, this is a straight line, okay? There's a straight line there on a log linear plot. Linear on the y, linear on the y, log on the x, straight line. This is that plots on a straight line, which is why we call it the straight line method. So if we look at this, right, and here you see why we said after long enough time, for large times, and again large is a relative term, so here you can see that at the beginning it doesn't work, right, but after some time the drawdown definitely grows as a logarithm of time, right, in a straight line when this is in log. That means the drawdown after some time, right, after this initial period that doesn't work, then after that the drawdown grows as a logarithm of time. This is what this means, right, straight line. Now the beauty of that is we can here now we can draw that straight line, and from the equations before, and I'm not giving you all the derivation, but we can calculate the transmissivity. Remember from last time, right? Transmissivity is what we measure first, and then very easy, right? Transmissivity is 0.18 or 0.2, whatever, 0.18 of Q, the pumping rate, and del is 10. Now what this is you take a decade on your x-axis, so a decade in time, so a log, you know, 1 log in time, and what is the drawdown change over that 1 log in time. So you just go back and look at, you know, how much it is. Here that would be, you know, 12, 13 or whatever in this specific example. Once you have your transmissivity, you can calculate your storativity. So the principle is the same as last time, right? We start with the transmissivity, plug in the numbers, measure or calculate it, then plug it into the storativity term, and calculate storativity. Now we have a new thing here, T star. Now T star is the intercept of that straight line. Again, remember at the beginning it doesn't work, right? And after some time it does work. So T star is that intercept of that straight line when it does work to the x-axis. So it's basically what the drawdown would be, right, if we started on that linear trend. Now we don't start on that linear trend, but after some time we do get there, okay? So measure T star from the data, measure delta S10, right, a log drop in time, or a log increase in time, I guess. You know, if you multiply time by 10, how much do you increase the drawdown? That's your delta S10, and that's all you need to know. If you have both those things, you can actually plug in and calculate. So here's an example. I'm going to do it by hand, and then I'll show you the result in the next slide. But if we assume this was linear from the beginning, right, where, well, this is not very good, but my mouse wants to go left somehow. Okay, let me do this again. I want to go down. Okay, this is not quite right, but you see what I'm trying to do here. Go down, go down, go down. If I had a drawing tablet, which I'm trying to get one, then I could do that better, but I'm doing it with the mouth, so it's not great. But anyways, we get some T star here, and then the time is, again, you take a log in time, regress it. So again, I'm doing this by eyeballing here maybe, and then here maybe, right? So if we regress this on the y-axis, we're here maybe, and here maybe, so 2.5 to 4 point something, so a bit less than 2. Okay, so del S10, this is del S10, delta S10 is going to be about, less than 2, 1 point something, 1.8, 1.9, I don't know. And the intercept here, well, this is 0.1, 0.2, 0.3, so I don't know, 0.34 something, okay? So in the next slide, we can actually do this a bit better. So here we have, again, 0.1, 0.2, 0.3, 0.4, here, here. So 0.4 is T star. And then del S10, again, you take a log on here, regress it, 1.8, so I was about right here. Okay, so now if we plug these numbers in, again, remember Q, it's 10 cubic meters per second, was it? Per minute? Yes, per minute, that's right. So 10 cubic meters per minute, del S10, this is time in minute, is 1.8, so we get 1 square meters per minute. And then we plug that in here, so this is going to be 1. T star is 0.4, so you plug all that in. R, remember, was 10 meters, right? 10 meters times 10 meters, 100. Plug all the numbers, get the storativity as 0.54. Note that this is not realistic for a confined aquifer, right? This is just made up data, so don't pay attention to that. This is not right, obviously, for a confined aquifer. It's just like made up data. Okay, now we should be able to verify this, right, using the method from last time, which is that curve matching Thies curve method. So this is exactly the same data. Here the blue dots. So same data as the previous example, but now notice that we have the log on both sides, right, like we did for the last lecture. So log drawdown, log time. So now they look like this, right? And we can match our Wells function, and this is a little hint for your homework, right? What you have to do with the Wells function, you can see here, this is the Wells function, this is the axis of the Wells function. So here I rescaled it so that your scales are the same on the x and on the y. Well, you can't see the x here, but the y you can see, and you can see that the x is also modified so that, roughly a log in x, you can sort of see it on the Wells function, is the same size as the log in y. Okay, so you can see this is roughly, right, the same as this. Right, so you have to scale your x and y so that they're actually the same scale. Obviously, if you don't do that, then they won't match, right? Now, once they match, again, this is on the right-hand side. This is done in MATLAB. You'll have those code soon. Now you can take your matching point at 1 and 1, and now you have to go read the value on the x and y, or the drawdown versus time data, actual data, right? So this is the 1 and 1 in the Wells function that we saw last time, and on the actual data, right? Now, what is that number? Here is a hint. This is what I used to actually match those two, and the match is not great here. I could have done better probably, but it's pretty good. So you can see that I had to modify my data, and I had to multiply time by 3.5, and I had to multiply drawdown by 1.2 to get that match, which means, because it's a 1 and 1 match, right, our time is probably 1 over 3.5-ish, right, and our drawdown is probably 1 over 1.2, which is about 0.8 here, and then about, well, if it was 4 here, that's 0.25 to 6 to 7, whatever. 0.25 is, I think it's, let's say it was 4 instead of 3.5 here. Right, that would be 0.25 and 0.8, which is, again, if you go and look at the axis of the actual data, what you have, right, 0.25, and again, this is just eyeballing it, so you can see it's probably a little more here, and 0.8 is about right. So, again, this is your matching point on the Wells function. This is the axis from the actual data. Now you can read here what they are. You can eyeball or be a bit more precise, but this is basically the two values you get. Plug that into the equations we used last time. So Q we know, 4 pi h minus h0 is 0.8, right? And you end up with a transmissivity of about 1, which is the same as we found for the straight line method, 1 square meters per minute. And then for the storativity, again, just use the expression from last time, plug in the values, right, and find a number which is close to what we got for the straight line method. So you can see that those two methods are actually exactly the same, right? So they're doing the same thing, just two different ways. Okay, again, don't pay attention to that storativity number. It's just, it's just a made-up example, so it's just way too high for a confined aquifer. It should be in the E minus 5 times 60, so yeah. This is too high even for a per minute thing. Okay, okay, so this was the introduction for the straight line method. Now I want to talk about the leaky transient data for a minute. Okay, so the first question is, what do we expect? Okay, so again, this is from chapter 4, right, from the flow lectures. We have a leaky confined aquifer. So the confined aquifer is down here. There's a leaky layer right here where water can come from the top. Leak through this leaky layer from the unconfined up top into the confined and on to our well. Okay. Now conceptually, so again, remember that Wells function, which is log Wells versus log 1 over u, which is again equivalent, right, or a proxy for drawdown here and time here. Okay. So as we pump the drawdown, again, remember the drawdown is how deep this water goes into your well. Whoops. Now, at the beginning, obviously we're sucking a bunch of water, so it goes down fast, and at some point stabilizes, and then the steady state, right, is somewhere down there, right? After a long time, everything stabilizes, everything is equivalent, and there's no more change in the drawdown. That's our stable level in the well. Now imagine for everything being the same, now we have additional water, right, at some point coming from somewhere else, right? There's a source there. Now that means there's more water coming into our well, which means our stable drawdown level should be what? Higher, right? It should not be as deep because there's more water available, basically. We don't need to make that much effort, or for the same effort, we don't need to pump that much down, right, for the same amount of suction, if you will. Right, so we expect that drawdown, that stable drawdown, the steady state, right, to be actually higher in the well, because we don't need to suck down this much, because for the same suction, now we have additional water flowing from that thing into our well. So the same amount of effort, now more water in the well, so now stable level higher. Okay, meaning again, drawdown here, stable level higher, drawdown is lower, right? Less. Again, the drawdown is this difference here. So our drawdown is less, right? This is the original. Now with the leak, we get a smaller drawdown in the well. So a smaller drawdown, if that was our original completely confined, now our whatever that is, right? Original S0 and then S leaky is S1 here. So again, this is S1 and this is, S0. So S1 is smaller than S0, so it's somewhere here. So we expect, so at the beginning they do the same, right? Because the leak doesn't influence at the beginning. After some time, it starts leaking and leaking and leaking and leaking and leaking and leaking. And now we reach that steady state somewhere below. Okay, so again, conceptually, that's what we expect. Good. Now, if we go back to the math, these are the equations, right? So leaky confined aquifer, remember this basic 1D equation in the regular coordinates, right, in the XY coordinates. So if we use a 1D version just with the X, this is expression. Again, this is the unsteady part, right, the change over time. And now we have that source sink term for the leaky case that we have to account for, right? So this is our leakage from the unconfined aquifer up top. Remember, for an unconfined, that could be the rain rate, for example, right? So this is the leakage or the recharge or the source sink that we have in the equation. Now for leaky aquifer, again, remember that this E term is basically your Darcy flux across that permeable layer or semi-permeable layer, and this is the hydraulic conductivity of that material, of that layer. This is the head across it, right, at top and bottom, and finally this is its thickness. Okay, so this is the Darcy flux across that layer. Now, if we write this in radial coordinates, again, I'm not going to go back to that. You can go back to a couple lectures back to verify how that works. And I'm sorry for all those switching around. Now we replace the E over T with the expression of E here into the equation. And of course, the transient part doesn't change, right? So this is the whole expression. Now we can write it as a function of drawdown instead of head. Remember that drawdown is basically minus H0 minus H. If we take H0 equals 0, for example, as a reference, right? Let's assume that H0 is 0, and S is basically minus H, right? So you have, you know, minus S plus S in here, right? Minus. And then that's it, and minus S, right? So now if we inverse all those, right, minus the whole left side, minus the whole right side, and that gives you this expression here, right? So we're transforming this to a plus S, so all the minus H's here are pluses, right? S, and then this becomes minus. Okay, and this becomes plus, and this is the expression on the right, right? S minus S, so minus. Notice here this is a minus, that becomes a plus. Okay, so minus plus, and then plus. Okay, so oops. Okay, so now we have this expression, which is the same thing, right? Just expressed as drawdown, because this is typically the data we have. Okay, so now we have a flow expression in the radial coordinates for a well in a leaky confined aquifer. And this is the partial derivative for the drawdown. Okay. Here's the expression for the drawdown, again, as a function of that new Wells function that has two arguments, right? So the time and then this new R over B. And again, B is an expression for basically the leakage across that formation. Or 1 over B is an expression for the leakage across the formation. Okay, so if we look at B here, there's two terms that are important. Transmissivity, which is the transmissivity of our confined aquifer that we're pumping in, and then K prime, which is the hydraulic conductivity of the leaking layer. Okay, so let's say transmissivity is really high. So our aquifer is really good, it's giving plenty of water. Okay, so if this is really high, then B is really high, then R over B is really small, and basically our aquifer works just like a confined aquifer, right? So just W of U of time, and then R over B doesn't really matter because this is so small that it's basically essentially 0. Okay. Now, let's assume that our hydraulic conductivity of that leaky layer is so small, right? It's so small that it's almost 0 or whatever. It's very, very small. Now again, T over K, right? 1 over almost 0 is a very big number, and now B is very big, right? And again, R over B, you know, doesn't matter. It's almost 0 because B is very big, so R over B is almost 0. So again, we're back to the regular confined case, which makes sense, right? Again, if there's a whole lot of resistance, so if there's no hydraulic conductivity, it's clay, let's say, and no water can go through, right? This K prime is very, very small. Again, this is very big. This now is very small, and we just have a confined aquifer. And then, of course, you know, the opposite is true. So if T starts to decrease, or K prime starts to increase, now B starts to decrease or be, you know, more in the level of here, and now we have to account for that second argument, which is basically we're going down those curves here, right? So again, this is the confined, so this is the Theus equation right here. Sorry. So this is the thesis curve, right? The one we've used last time, and I did another example today. And this is the family of curve as, you know, R over B increases, meaning B decreases, right? So again, go back, but if transmissivity decreases or leakage increases, then, you know, we're going down those curves, and we have to find where they match. Okay, and that's what we'll do essentially in the next lecture. I'm just showing you here real quick, right? But now we have a family of curve. This is an Excel/MATLAB, you know, version that I have that I'll describe on Wednesday. But we can see that if we have real data from a leaking aquifer, right, now we can match that data to this family of curve instead of just the one curve that we had, the thesis curve up top here. Again, remember that this is the thesis curve on the top when there's no leakage, basically. Oops. But if we are looking at real data and we see that it doesn't quite conform to the thesis curve, but there's definitely some lower drawdown, right? There's some leakage, there's some recharge somewhere, then we can match that to a family of curve. And again, I'll show you an interface that I did in Excel that can account for this. Okay, thank you, and I'll see you on Wednesday.